guys, so here we're going to talk about how batteries work, or really something called cell potential. You'll need your notes, as well as something called the standard reduction potential table. It's probably in your packet, so look for a really long table. If you don't see it, you can just kind of look off of what I have right now. So we're going to talk about what cell potentials are, something called anodes and cathodes. We're going to determine what the cell potentials are for half reactions, and overall cell potential. So none of that makes any sense, and it's okay. We'll after this video. So here we have a little scenario. We have two beakers, one on the left-hand side, one on the right-hand side. Inside of each of those beakers are going to be a piece of metal. They're connected by a wire with clips, and in the middle we have something called a voltmeter or multimeter. Connecting the two beakers, we also have something called a salt bridge as well, and those salt bridges help for a flow of ions. So if you notice here, one of the metals has a label called the anode, the other has a label called the cathode. Those are locations of, again, kind of where certain things happen. We'll explain that in just a bit. And you'll notice here that the electrons were going from the anode to the cathode. So we're going to explain what that occurs, or what happens here. So cell potential is, technical definition here, measure of potential difference between two half cells or half reactions in an electrochemical cell. Pretty much what it means is the flow of electrons from one half cell to the other, so one beaker to the other, or one metal to the other. So this is measured in volts, or voltage. You've seen this before, like a 9-volt battery. So you have 9 volts of kind of going from the anode to the cathode, and that's just pretty much a flow of electrons. And you'll go more in depth in this when you take physics as well. So electrons flow from one cell to another cell, and again, it's measured in voltage. There's a calculation that deals with it too. So to figure out how much flow of electrons are going to be occurring, we have a really simple calculation. The E cell is equal to the E cathode minus the E anode. So really it's the cell potential is equal to the potential of the cathode minus the potential of the anode. And these values will be given to you on a table. You just have to look for them. So let's talk about the labels, the anode and cathode. So over here on the left-hand side of the picture, we saw that the anode was there. An anode is where oxidation occurs, and we use the little kind of saying anox to show that an anode is where oxidation occurs. For the cathode, we use red cat. Reduction is at the cathode. And electrons will always, always, always flow from the anode to the cathode through this wire. And what that voltmeter does, or multimeter, is measures how much pretty much how many electrons are going from one side to the other side. So this is your standard reduction potential table. It's all at standard conditions, 25 degrees Celsius, 1 molar. And you'll notice this is all reduction. All of these have electrons on the left-hand side. And the biggest thing I want you to look at is that if you're looking at something that's undergoing oxidation, so say for example you have Zn solid, produces Zn plus 2 and 2 electrons, I want you to find, well, you know that this is undergoing oxidation. All of these values are based upon reduction. So if you're trying to find this chemical equation, flip them. Make it go Zn plus 2 electrons produces Zn. All right, and that should look like a negative. So you can eventually find that in here. All right, in fact, you'll find it right there. And it has a standard reduction potential of negative 0.76. So when we look at these, we're going to kind of check out what these values actually mean. So here I've taken Fe plus O3, or excuse me, Fe, well, actually, you know, I'm going to give you a different one. I'll give you an easier one. How about this one? We'll take a look at Zn solid plus Cu aqueous produces Zn plus 2 plus Cu. We've seen these before. We've already done the half reactions for them, so I've listed them for you. So this is the overall reaction, and these are each of the half reactions. So take a second, go ahead and figure out which is oxidation and which one is reduction. So hopefully you remember this. Zn solid produces Zn plus 2 electrons. These 2 electrons are in the products, so this is undergoing oxidation. Here, since your electrons are in the reactants, it's undergoing reduction. Remember reactants, reduction? So those electrons are in the reactants. So let's use our other new little saying that we learned today. So we have anox and red cat. And that's supposed to be a D there. So anox means the anode is where oxidation occurs. So this will be our anode. And red cat means reduction occurs at the cathode. So this will be the cathode. So the Zn solid is your anode. The copper +2 is your cathode. So let's plug them into this little equation right here. We want to figure out if we put zinc in one beaker and copper in another beaker, what the flow of electrons are going to be. So let's find these equations inside of this table. So remember, this is all based upon reduction. So all the electrons will be on the left-hand side. If it's something that undergoes oxidation, just kind of flip the equation. So we find and skim through it. Let's see. The Zn +2 took me a few seconds. Zn +2 electrons produces Zn solid. Well, this is going to be the oxidation at the anode. And that value is a negative 0.76. So for the anode, that's a negative 0.76. And let's go ahead and find the Cu +2 electrons. Now there's a few Cus in here, so make sure you're using the right one. And there we go. That one matches up. Cu +2 electrons produces Cu solid, and that's 0.34. And they're all measured in volts. So that's our cathode because we knew it underwent reduction. So it's a cathode minus the anode, and I'm going to put that anode in parentheses. So since you have a minus a negative, it's going to be 0.34 plus 0.76. And when we add them up, 1.10 volts. So overall, 1.10 volts will flow through the wire, or you'll have that many electrons essentially going through the wire. Compared to a 9-volt battery, this is pretty weak, but still not too bad. It still would operate some things. All right. If you ever, by the way, end up having a negative value, that means that this is non-spontaneous. Since it's non-spontaneous, you need some sort of battery to make it actually happen, to drive that reaction. So make sure that you also take a look at that. So since this is a positive value, the higher the value, the more spontaneous it is. It will occur all on its own. Like those electrons will flow, just put the wires there and they'll flow on its own. If you end up having a negative value, that means those electrons won't flow. You have to put a battery there to make the electrons flow. So this is something that I'm saying out, I'm not writing it out, so make sure that you've written this out for yourself as well. And we'll see who's actually paying attention on the videos or on the notes. So to quickly summarize, oxidation occurs at the anode, reduction occurs at the cathode, and use that table of cell potentials to help you out. Have a great day, guys.